Okay, let's get going with lecture. Get your clickers ready. I guess Darian is absent today. But let's keep going. Next Tuesday, a week from today, we have exam 3. And it will be covering topics from lectures 19 through this Thursday, lecture 24. Today is lecture 23. And on that note, let me just remind you that our grading strategy of drop your lowest exam score, keep your best 2, executes after exam 3, because then we'll have 3 exam scores. And most of you do have 2 exams already. So if you're there for exam 3, you'll be in good shape. All right. And you can choose from that. So we'll keep exam 3. If exam 3 is greater than either exam 1 or exam 2, we'll keep exam 3. We'll drop the other one, the low one. And the one that it's greater than, and then we'll keep the other 2. And then your midterm exam scores are final. Right now, almost everybody's got 2 midterm exam scores on the books. All right, but that's changeable because of exam 3 coming up. Right, you can still calculate a grade. 100 points for exams, 25 points for clicking, 25 points for HW. But until we do exam 3, it could change drastically. So study accordingly. Be ready for exam 3 next Tuesday. And it will contain it will be here in lecture hall. And it will contain some clicking and some Scantron dots and so forth as usual. Okay, questions about any of that? Yes. When is the final? What does the syllabus say? May 6th? April 26th. Yeah, whatever the syllabus says, that's what you go with always. Okay. And for us, it's at 10 a.m., correct? It's at 10 a.m.? My other class has a 7 a.m. exam. Hoofta. All right, any other questions? Okay, let's keep going. We started talking about waves. This is one of my favorite photos. It's a place called Praia do Norte in Portugal, and it happens to be a place where when the wind is right, there's an underwater canyon that funnels the water when the wind is blowing past England and towards Portugal in just the right direction. Certain times of the year, the waves get ginormous. This thing it's got to be 100 feet high. And look at these people. Look, these people are up here in this building right here. These guys up here on the parapet, they're in a building on top of a cliff, and they're barely looking down at this guy. So they just get some amazing waves there. And we're going to be talking about waves for the next couple lectures. Basic wave concepts. This is the thing that is, I think, the most important about waves, that they transport energy and momentum across space-time from space-time location A to space-time location B, but they don't necessarily transport the atoms and molecules of the medium in which they're moving. And some waves don't even have a medium. Electromagnetic waves, they don't have a medium. Water waves, water is the medium of surfing waves. And it's the medium of this photograph here, waves in a little, like waves in a pond. circular waves. But electromagnetic waves don't really have, they're not embedded in anything, but they transport energy and momentum. So what this means is that, one way you can think about this concept that they don't transport matter necessarily is that when there's a storm off the coast of West Africa, we might get some waves over here in Florida. Right now, those waves that race across the ocean for Florida that you end up surfing or swim, body surfing, whatever you do at the beach for fun. That's not water from the coast of West Africa. That's water that's in the the Gulf Stream there, right off the coast of Cocoa Beach. All right, but somehow what happens is the energy is transported. And the momentum is transported. So remember, in space-time considerations, energy and momentum, you have to always think of them together. So, yeah, waves transport energy and momentum, but not necessarily material particles. Now, the exception of that is something like an ocean wave, where if you have like a rowboat or a raft or a message in a bottle, the waves will eventually get it, but it could take centuries to get across the ocean, because it'll go all different random directions and stuff. So slight motion, but the wave itself we consider as not really moving that stuff. Another wave phenomenon that I'd like you to take a note on, sound. Sound waves. Sound waves are waves in the medium that we call air. And a sound wave is a small variation in the pressure, in the atmospheric pressure. So like the atmospheric pressure today is like, 29.7 inches of mercury, like 1,002 millibars of air pressure. And what sound is, it's little teeny variations, it's like 1,002 up to 1,002.1 millibars and down to 1,001.9 millibars. And then back up to 1,002.1 millibars and back down to 1,001.9 and back and forth. And that kind of variation in the pressure you detect in your eardrums. And basically that pressure variation causes your eardrum to rattle at a specific rate. And that rate at which your eardrum rattles is the frequency of the sound that you hear. Okay, so a really deep bass note might be 100 pressure waves per second banging against your eardrum per second. A really high note might be 400 or 500 pressure waves per second. So if you know somebody in the choir that can really hit, high C or higher than that, they're putting a lot of pressure variations, the pure note anyways, a lot of pressure variations, at a very high frequency compared to somebody, you may know somebody else that sings bass or baritone in the choir. And they're down here like this. And I can't really sing that deep, but you get those low notes, and the lower it goes, the fewer vibrations per second that bang into your eardrum. And of course, your eardrum triggers the nerves in the inner ear, and then those nerves transmit information into your brain, and your brain perceives it as a sound. And hopefully it's a nice sound like somebody singing. All right. Another thing about waves that's pretty important and is actually important for quantum mechanics, which is what we're looking towards, is that waves are not easily localized, usually. All right, so if I say a wave, it's hard to, if you're out there in the ocean, you can point to a particular wave, but really it's a train of waves, peak after peak, trough after trough. And they're all coming, and they're all, going to be very close to the same. Electromagnetic radiation, it's the same thing. You're setting up an oscillation in the electromagnetic field, light, electromagnetic radiation. But it's very hard to say that it has a certain location, like a baseball. The center of mass of a baseball, the center of mass of a suitcase, center of mass of a horse, the center of mass of a big truck. You can figure out the location in various methods of that point. But for a wave, it doesn't have a center of mass. I mean, it transports energy and momentum, but it itself does not have a defined mass. So it's pretty unusual waves if you think about it. Now let's take a look at the different parts of a wave. Go ahead and make some sketches, and this is going to be your baseline sketch. Okay, and I should have made this a little bit bigger, but right here where you see my cursor next to the number 0, think of that as sea level. And then think of this up here as the peak of an ocean wave. And then down here, and when you're out in the ocean, sometimes you're in the, I read that they had this storm here a week ago or so out off the coast of Massachusetts, and it was sending big waves, 9-foot waves here in Florida, but up there they were, up off the coast of New England, they were 30-foot waves, and I was thinking to myself, man, that must be frightening to be in the ocean with 30-foot waves, and that's, from the bottom of the wave to the top of the wave. Oh my goodness. Now, every wave has a speed of propagation, all right? And so you can draw an arrow at the top of this part of the wave, all right, this peak. And let's say that it's moving to the right, and that would be the propagation speed v. Now, the propagation speed of sound is about 340 meters per second. Plus or minus, so that's about 600 miles an hour, 700 miles an hour. And it varies with the atmospheric pressure, humidity, and stuff like that. If you've ever been out by a lake in the early morning or late in the evening, sometimes you can hear really small sounds from a mile away on the other side of the lake. And that's because of the atmospheric conditions that affect the propagation of sound waves. But in general, they're all going to have the same propagation speed. So make another arrow over at the second peak and make an arrow the same size down here at sea level or equilibrium. That's the equilibrium position. That's where the ocean would be if there were no wind. Just be nice and flat. So you can think of that as sea level or equilibrium. Down at the bottom of the trough, the wave is moving off to the right. And usually they move at the same speed. Now, certain waves through material media, like in the surface of the sun, or here's something that they don't always travel at the same speed. Any kind of an explosionary wave, a detonation wave. Those sometimes, one part of it's faster than the other. But generally speaking, simple waves like ocean waves and stuff, electromagnetic waves, they all move at the same speed. Now, these different parts of a wave have a name. The peak is the different positions in the wave are called phases. All right, so the peak is a phase. The trough is a phase. The next peak is a phase. And you can go, this intermediate point, sea level, is a phase. A descending waveform at equilibrium. Okay, then this one over here across the way here where my cursor is now, that's sea level, but it's ascending from left to right. Question?
So is it peak and then the bottom is the trough?
Yeah, this is the trough. Okay, this is the peak. This is the next peak. And the next trough is out of the picture. But, you know, it would be out there. And this is like intermediate point here. And those points on the wave are moving, so you don't really say, well, that's, you know, the left, or that's the center of mass of the wave. It's not. You know, that peak is in motion. It's passing through all the different atoms and molecules in the sea. All right? So we don't really call it a position as so much as a phase. Okay? And here's another thing that we like to compare waves to. The phases repeat. Okay? Peak, trough, peak, trough, peak, trough in a wave. And usually it's a regular variation. It's an oscillation. And so we compare it to a circle. And you know, everybody knows that the radius of a circle is 2 pi r. So if you go 2 pi r around a circle, then you're back to where you started from. And you go another 2 pi r, and you're back to where you started from. And it's kind of like what waves do. So we frequently give a number between 0 and 2 pi to the peak, and then a similar number, but different, to the trough. So in this sequence here, you could call this first peak up here 0, and then this one down here would have a phase of pi. Okay? A phase angle of pi. And then this next one up here would be a phase angle of 2 pi. You know, because it's one full variation, one full wiggle. Now, you can start your phase angle right here at equilibrium. You could have started with 0. And then this next phase equilibrium here would be pi. And then this point over here on the far right would be 2 pi. So you can start it wherever you want. Just, you know, try to be consistent. But that's a terminology that you sometimes see, phase, to describe points on the moving variation of a wave. Now, make yourself another sketch. And let's talk about wavelength. Now, the wavelength of a wave is right here, from peak to peak. And most of the time, waves are pretty close to identical. Now, out in the ocean, there's all kinds of currents, and there's fishes in the sea, you know, and there's wind and stuff. So you don't have perfect variation of waves. But a lot of times, they do look really similar, peak to peak to peak to peak for miles. All right, and so you'd have a real regular wavelength. You don't have to measure peak to peak. You can go from equilibrium to equilibrium, like right there. Go ahead and draw a dotted line there. From the first rising equilibrium point to the next one, rising as you go left to right. All right, that's a wavelength. The symbol for wavelength is Greek lowercase lambda. You could do a wavelength right over here. Ding. From descending to descending equilibrium points. That's a wavelength. This one right here in red, that's a half wavelength. All right, so sometimes that's nice to be able to think about, okay, that's a half wavelength, not a full wave. Question? I've got a picture of it. It's kind of it looks like an upside down Y. I'll give you a picture of it in just a second. Okay. In fact, I have it coming up. Now, draw yourself another picture. Baseline picture. We got a little bit more anatomy to do for waves. Now, that was the sideways, or the sideways spatial in the direction of propagation wavelength. The other one is your variations away from sea level. So vertical variations, we have a word for that. Now, the amount of a wave right here from sea level up to its peak, we call that the amplitude. All right? Now, that's usually what scientists talk about, wave amplitude. And I'll talk about why that is in a minute. But if you listen to the, like I was mentioning, the weather report on WFTV, Channel 9 Eyewitness News, all those guys over there, they were talking about wave height. Now, what the wave height is this, kind of distance from the trough vertically up to the peak. And that's your wave height. All right, so kind of sketch those in for your anatomy. All right, now that's for an individual wave. Another thing that waves do is they interact with other waves, and they interact with regular matter. So one of the things that waves produce is something called wavelets. All right, they behave way differently than a Newtonian particle. Now, on the first day of class, did we look at the diffraction gratings and the different light on the first day of class? The diffraction gratings this is what the diffraction gratings do. The light goes in this case, the waves are coming in from below, and they go through that tiny opening, and then it's like little new spherical waves are created right here in the gap. Those are called wavelets. Because on the other side of the gap, when those original waves, they look nice and flat coming in, this is an overhead picture. So they're moving from bottom towards the top. But they hit that gap, they hit the solid part, and they just get reflected backwards. But they hit the gap and they go through, and as they go through, they kind of curve out. Okay, that's called diffraction, and that's a wavelet phenomenon. Okay, and it's and it happens at the edges of barriers, gaps in a barrier. Sometimes it even happens when you go from different density to a new density. You get diffraction. And so there's, and that's another way of saying that is interference. Go ahead and write down that vocabulary word. Interference is going to be real important for us when we try to study molecules. The interference of waves. And this diffraction picture is a picture of wavelets interfering with each other. Okay, and producing that unique pattern. So the pattern on top of the barrier, after it passes through, is way different than the pattern below. Right? And the diffraction grating that you guys looked through was similar to this, except it had a zillion little openings, not just one. This is a simple picture of diffraction. The diffraction grating has, a zillion per millimeter, like several hundred per millimeter. But you get wavelets like that with diffraction gratings. Another simple thing about waves is the wave equation. Now this one's pretty simple. And there's lambda. V equals lambda F. See how that's kind of a upside down Y? Okay, Greek lowercase lambda. Now let me move my picture up, and we'll talk about wavelength. Now wavelength, lambda, is the spatial distance between two waves. So peak to peak, trough to trough, etc. And we just had a picture and diagram of that a few minutes ago. All right, so make a note of that. This is the English language sentence. We had some diagrams of it just a minute ago, wavelength. So the spatial repetition distance for waves. The period is the temporal interval between waves. So this is the amount of time, you start your watch, your stopwatch, when a peak passes you, and then you stop it when the next peak passes you. That's the period. Okay? The temporal interval between peaks. Or you could say the temporal interval between troughs. Or the temporal interval between rising equilibria, etc. And the frequency is 1 over that. Okay, so we have a space-time measurement of period and wavelength. And then the frequency is 1 over the period. And so the wave equation, V equals lambda F, is wavelength times the frequency. Now, the frequency, the unit of frequency, you better write this down, it's not in the notes. The unit of frequency in the metric system is Hertz, Hz, named after a German scientist, Professor von Hertz, not the rental car company, but a German guy, pretty smart guy. He was the first one to produce electromagnetic waves and measure them in the laboratory. So they named the unit of frequency. And a hertz is 1 wave per second. Let me repeat that. 1 Hz equals 1 wave per second. A 1,000 waves per second is 1 kilohertz, kHz. AM radio, so if you listen to WDBO, ESPN radio 580, that's 580 kilocycles of electromagnetic waves every second. 580,000 waves per second. FM radio, the next big unit, go ahead and write this one down in your notes. 1 million waves per second is a megahertz, capital M, capital HZ. And FM radio operates, excuse me, whew. I had a long night getting my exam ready for the astronomy kids, so I'm really sleepy. FM radio operates between like 88 megahertz and, 100 and something megahertz. Okay? Capital M, capital HZ. So that's a million. So like, if you're listening to 88.5 FM, whatever station that is, that's 88.5 million electromagnetic waves per second hitting the antenna of your car. That's what it is. And it causes the electrons to oscillate in the antenna, and then they cause a little bit of current, an oscillating current in the rest of the circuitry, and that gets translated to the microphone or to the speakers, and you hear whoever is talking or singing or playing music on the radio. So let's talk about electromagnetic waves, light. Special kind of wave. Now, light is a wave in the electromagnetic field. And so that means it is the same physical field that affects compasses and electrons and protons. So electrons and protons are the smallest electrical charges in nature. They're equal in size but opposite. An electron is -1. Proton is +1. They attract. That's how the atoms stay together. The hydrogen atom is 1 proton and 1 electron, and what keeps that electron in orbit is the electromagnetic interaction. Okay, compasses are magnetized pieces of steel or some other metal that responds to Earth's magnetic field. And, you know, it kind of lines up with the direction of the magnetic field of the Earth. Did you know that the magnetic field of the Earth is constantly changing? And that in centuries, millennia, millions of years in the past, we can see from the magnetic alignment of rocks under the ocean, for instance, that we know definitely the age of, we can see that all the iron molecules in those rocks under the sea have flipped directions several times. So the North and the South Pole have flipped over geological time, not in our lifetime, but it is slowly moving, you know, and so it's going to be interesting in the next few hundred years to see what the Earth does. Now, electromagnetic radiation, the electromagnetic field forms a spectrum. And here's a nice little diagram. And if you type in electromagnetic spectrum in Google, you'll see about 6 million different variations of this diagram. And you may like other ones better than this one. This one's fairly good. All right. At the biggest wavelength out over here, this is important, bigger wavelength means lower energy. Tighter wavelength means really big energy on the left of this diagram. Right now, out here to the right, that's radio frequency, and then microwave and infrared. And there's no hard and fast boundary line for any of these classifications. So what one person calls radio, another person might call far infrared. What somebody calls microwave, you know, another, you know, like some guy that has a radar, you know, like in the Navy, all the ships at sea, they have radars and stuff like that. He might talk about microwave wavelengths, or he might talk about infrared. Somebody else might talk about the same frequency as infrared. Now, on the tight wavelength end, right, look how tight these waves are down here. And that's kind of an exaggeration. It's even tighter than that, but it gives you a flavor or an idea of the tightness. Now, tight wavelengths means small wavelength. That means the frequency is a lot higher, right? And so out there are X-rays and gamma rays. Gamma rays are the highest energy that there are. The ones that we can see are usually from space, although we can create them in the laboratory and in a nuclear reactor. Matter of fact, the idea, you may have heard on television this TV show called Star Trek. You know, with Captain Picard and all those guys, and Captain Kirk and Spock. And they have matter-antimatter engines. You know, the dilithium crystals and all that stuff. Now, matter and antimatter are real things. Let me repeat that. Matter and antimatter are real things. They're not science fiction. We don't know how to make an engine, you know, to run a starship from matter and antimatter. We don't know about actually, we do know about dilithium crystals, but so far we haven't used them to make a matter-antimatter engine. But matter and antimatter, when they annihilate, and they form energy frequently it's gamma ray. And a lot of times it's X-rays. A little bit of matter and antimatter annihilate, produce electromagnetic radiation in the X-ray region. Ultraviolet is not quite as tight. So here's ultraviolet down here, and it's a lot tighter than radio, a lot shorter wavelength. By the way, the wavelength is why small wavelength for like X-rays is why X-rays can penetrate your skin and take images of your bone. It just zaps right through all the molecules in your skin. But bone molecules stopped X-rays. And that's why, you know, the X-ray images show bones, but they don't really show any of the soft matter, soft tissue in your body. A little bit sometimes. depending on the flavor of X-rays that they use. Question? Yeah, MRIs are a little bit different, but CAT scan I think is an X-ray process, but magnetic resonance imaging (MRI) that's different, and it's a different process, and for that reason you can look at different things with MRI. You know, CAT scan different from MRI. So we try to use all these things in here. Okay. I think MRI is down a little bit further down here. I should look up I'm not a big expert on MRI. I should be, though. I should look that up. I'll try to look that up for the next lecture. Thank you for bringing that up. In between ultraviolet and infrared, strong ultraviolet, weak infrared, big wavelength infrared, tight wavelength ultraviolet is the visible band. Okay, so radio, infrared, and the visible band. Now, there's a famous scientist that donated his name. He's no longer with us. His name is Roy G. Biv. And he donated his name. You know how people, when they die, they donate their body to science? Well, he donated his name to science because his name is the exact order of colors in the visible spectrum. Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. This is kind of a famous, so he became famous just for that. Okay? And so it's a way for you to remember a famous scientist, and his full name gives you the order of the colors, from red all the way up to violet. Now, something that I'd like to point out to you that I was talking with some friends about the other day. Raise your hand if you are either an art major or you consider yourself artistic. Okay, that's a good number of you. It's good. Right now, those of you that are art majors and everybody else, I want you to think about this. Roy G. Biv. When you're in art class, you think of a color wheel, right? It goes from red to orange to yellow, green, and then to blue, indigo, violet, and then the wheel turns back to red. It goes from violet to red, all right? But that's not what this is. In nature, there is no color wheel. The color wheel is it looks like that to us. It's like an aspect of our brain that we think of a color wheel. But this is what color really is. So I want you art majors, think about this. Beyond R is infrared. The other direction, beyond violet, is ultraviolet. And we can't perceive them as a color, but we ought to think of them as a color. Ultraviolet, a purple even deeper and more purpley than the deepest purple that you've ever seen. Infrared, even redder than the reddest cherries. Redder than anything. And more colors after that. So we think of a circle, but it's not really a circle. It's infinite range. Just think about that. What are those colors? And here's something else. Humans, we can only see from about 400 nanometer wavelength for violet up to 700. Go ahead and write that down. 400 nanometers to 700 nanometers. 400. So Roy G. Biv is, the infrared edge R is 700 nanometers. The ultraviolet edge V is 400 nanometers. Now, they say that some animals like bees can actually see in the a little bit deeper into the infrareds than we can. All right? So it'd be kind of interesting to, to figure out what the color wheel would be for a bee, And I heard that deer also can see in the infrared. Now, I'm not sure if that's correct, but I do know that different animals can see a little bit deeper into the infrared. I don't know about ultraviolet, though, but definitely infrared. And, we have optics. Did you know that silicon, a silicon crystal in Roy G. Biv, it's completely opaque. So if the silicon that goes into your computers, your phone, everything, all that silicon, it's based on solid state silicon. That stuff is opaque to visible light. Roy G. Biv, reflects off it but doesn't penetrate it. But you know what does go through it? Infrared. So when we want to have infrared optics, like Army soldiers in the Army that have infrared goggles and stuff, the optics that they have are made with stuff like silicon that will focus infrared light, just like we have eyeglasses and binoculars to focus visible light with glass. So it's kind of cool. So here's the other range. So radio all the way to X-ray and gamma ray. The speed of light, we're going to do this, some calculations with this in a minute. The speed of light is pretty fast. It's not infinite, but it's almost as if it's infinite, for us humans anyways. But for stars, it's not infinite. The Earth is about 8 light minutes away from the sun. So relative to the sun, on an astronomical distance, the speed of light is nothing to write home about. But for us, it's pretty fast. 3 times 10 to the 8 meters per second. That's 300 million meters per second. All right? And we measure distance to other stars in light years, and light hours out to the outer part of our solar system. So let's talk some more about light. Light is an electromagnetic field. Look at that beautiful photo. Sunlight. Every time you see a beautiful dawn like that, you can think about Roy G. Biv and all the other colors. The sun produces ultraviolet, plenty of it. That's what gives you sunburn. Infrared too. All right. And it's basically an electromagnetic field that oscillates. In other words, it waves. It itself waves. So let's talk about this particular question. Why do physical systems oscillate? Simplest example, and the classic example, is a spring, like this one here. This is an automobile spring, kind of a fancy one. All right. Now, the force law that, oh boy, my thing just, hold on a second. I got to re-log in here. It just signed me out of this computer here. Okay, I gotta figure out my password here. Oh man, I hate this caps lock business on these crappy, excuse me, Excuse my French. These Windows computers drive me bonanza. All right, here we go. Let's try this again. Okay. Okay, the force law, you know, this spring here, this photo of it is taken at equilibrium. So it's neither stretched nor compressed. You know, if you compress a spring, it'll push back on you. If you stretch a spring, it'll pull back on you. Okay? But you can, you know, if you just set it there and let it rest, that'll be the equilibrium length. And so the force law depends on how far away you are from the equilibrium position. So it's proportional to x, you know, position x away from the equilibrium position. And it's a restoring force. So if you if you move the spring to the right, it gets a pullback force to the left. If you crush it inward to the left, it has a pushback force to the right. You know, so depending on, you know, whether you're compressing it or not. All right, so this image here, so let's take a look at this. This is, let's say that this vertical line here is equilibrium x subscript 0. All right, and so when the red block is there, you know, there's no push or pull from the spring. That's the equilibrium position. But when you pull it out to the right, say to right here, position X, when you've pulled it out there, the spring is going to pull back to the left. All right, so you get a leftward pull. All right, so try to make a sketch of that if you can. All right, so you get a leftward pull. So that's what it means to be a restoring force. Movement to the right brings out a pull back to the left. Motion to the left, which would be compression, in this diagram anyways, brings about a rightward force. Okay? So the formula for the restoring force, the spring force, is very, very simple. Write it down. F equals minus kx. The minus sign is what makes it a restoring force, because when x is positive, minus kx is a negative number, and that means it's a force to the left. When x is negative, negative times negative is positive, the force will be a positive number. That means it's rightward. Katia.
In the first picture, if you pull the block out to the right,
If you pull the block out to the right,
the spring will,
pull back to the left. Yeah, the spring will pull you back. It wants to bring it back to equilibrium. If you pull it out to the right and then let go, it'll go right back
also like the square is like attached
to the spring. Yeah.
and
And it's movable. It can slide back and forth. Yeah. It's not a rigid lockdown structure. It's like a weight that can move back and forth. Students, when the force law is F equals minus kx, or if the potential energy is 1/2 kx squared, and frequently we see that, you have an oscillating system. All right, so, and that's what I want you to know about springs for now. Right? Anytime you see F equals minus kx, or anything like that, minus positive number times some amplitude of distance or anything, it's going to be a restoring force. Question? No, I can't. We're going to keep going. Get it from the YouTube. We got a lot of stuff to cover. All right. So let's do another look at, Katie, a moving objects, and this might help you out because this is similar to the previous slide. Yeah, we'll get it. Let's talk about one full cycle. Now, basically a full cycle of a spring system, an oscillatory system, is 4 journeys to or from equilibrium. Now let's go through it. You can see them all in this diagram. All right? Now if you start at equilibrium and then you move to the right, you're going to experience a leftward force. So when you're over here, all the way out to the right, at some point, that spring is going to turn you around and start it's going to start bringing you back to the left. Okay? So you're going to move back towards equilibrium. All right? And so that spring is trying to restore you to equilibrium. But if you're not interfering with it, it's going to overshoot. Okay? So it's going to get to the equilibrium point, so that's right here. But it's going to keep on going because it's moving. It's not going to stop if there's no friction and stuff like that. So it's going to keep going this way. So there's the third segment from equilibrium to the left side now, and we're compressing the spring. Okay? And now and you can see what happens to the spring. Here it is. When you're out here, that spring is compressed really tight. And so that means, dude, that spring is pushing back to the right now, back towards equilibrium. No matter where you go, the pullback or the pushback force is always back towards this center location, equilibrium. So here's the return trip. Now look at that. That's 4 trips to or from equilibrium. First is the first big arrow here from equilibrium to the turnaround point. Second black arrow from the first turnaround point back to equilibrium. Then the third arrow is from equilibrium out to the inner turning point. Okay, so this is the outer turning point. This is the inner turning point right over here. And so the fourth segment is from the inner turning point back to equilibrium. And then you do it all over again. And then it'll just, because that's what a spring system does. It'll go beep, 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 back and forth, left, right, periodic. I mean, if it's a good spring. Right? So that's one full cycle. 4 journeys to or from equilibrium. Now, they all add up to one full vibration of the system, or one full cycle. Now, this is a really good diagram to show you what I say about amplitude. Because mathematicians and scientists are inherently lazy, but because they know trig and calculus out the wazoo, they use the amplitude of the wave for all the mathematical formulas that they need. And there's a lot of trig and calculus and stuff, so we're not going to get into the nitty-gritty of that. But that's why we have this term amplitude. Because it turns out that the full variation left to right is not as handy as half the variation. The absolute value of the variation left and the variation right. So now let's take a look at waves in the sea. All right, so wave top to sea level. Here's sea level right here, calm sea. And we've talked about this. Here's the amplitude. And this is the amplitude too. All right, so that's a bunch of different waves. It's good. And here's the interesting thing for us to think about. That it turns out that for the electromagnetic field, the energy per second is proportional to the square of A. You know, so the electromagnetic field is wiggling. It's getting stronger. You know, it's pointing up, it's pointing down, weaker, stronger, up, down, up, down. That amplitude of variation is the square of that is proportional to the energy. And that is why the electromagnetic field is an oscillatory system. Now, let's use the electromagnetic wave equation. Here it is. C equals lambda F. C is a special symbol that we use for the speed of light. Now, in general, the generic symbol is V equals lambda F, you know. But if you're talking about light, we'll just use the symbol for light. C equals lambda F. Okay, so lambda is the wavelength. F is the frequency. Now, take good notes because you're going to do a calculation with your eye clicker here in just a second. All right? So the wavelength times the frequency is the speed of light. The speed of light is a constant. That's one of Einstein's laws of relativity. So the wavelength is spatial. So that could be measured in centimeters or meters, kilometers, feet. I mean, Sir Isaac Newton probably worked in feet. Period is temporal, so seconds, and therefore frequency is 1 over that, hertz. And so yeah, that's the basic equation. Now, what we're going to do together right now is calculate a frequency for a red color, which I happen to know is 656 nanometers. Now, if you have forgotten, a nanometer is a billionth with a B for Bravo, a billionth of a meter. So 656 times 10 to the minus 9 meters. And what we're going to do is calculate the frequency. So here's our move. We're going to change C equals lambda F, and we're going to get F by itself. Okay? So that's basically just C divided by lambda. Okay, we're going to divide by lambda on both sides. Okay? Good? All right. You know, and if you want to get the wavelength, and if you have the frequency, you want to get wavelength, you could use this. C over F equals lambda. But we're going to do the first one. C over lambda equals F. All right? And it's not a bodacious, you know what's bodacious about it is all the scientific notation. So let's go through it nice and easy. Nothing but net. All right, here we go. Numerator, C. Denominator, lambda. All right, so 3 times 10 to the 8 meters per second in the numerator. And 656 nanometers. Okay, remember, a nanometer is the same as 10 to the minus 9 meters. Okay, so this baby here in the denominator, that's a nanometer. But I want to cancel meters up here in the top. See, the speed of light is meters per second. I want to cancel that, so I'm going to convert from nanometers to regular meters, but then I have to put in 10 to the minus 9. All right? Now, 10 to the minus 9 in the denominator is same as 10 to the regular 9 in the numerator. So I can write it as a 3 divided by a 656 and a 10 to the 17 on top. My meters cancel, top and bottom, but I still have, up in the numerator, I still have per second. All right, now that's a hertz. That's like a per second, or a 1 over second is a hertz, Hz. Now this thing here, if you're on a calculator, you could calculate it out this way. 3EE17 divided by 656, all right? And I know on an iPhone you can do the iPhone calculator. On your Mac laptop, you can do the same thing. But if you have, like, you know, a TI, it might look a little different. But I highly suggest that everybody in here get a little bit of practice with scientific notation. All right, because you're going to need it. All right. Now, 3 divided by 656, that's like 4.5 7, and then 10 to the 4. So we're losing a little bit of the 10 to the 17. And so if you do that on your calculator, you get 4.57 EE14, which is the same as 4.57 times 10 to the 14. Now, when you're doing the calculation in just a minute, you're going to be doing this on your own. I'm going to ask you to convert this answer that you can get from your calculator into terahertz. Now, a terahertz is the same as 10 to the 12th hertz. And so go ahead and jot this down. We're going to go through it. This answer is the same as 457 terahertz. All right, now I'm going to show you why that is. All right, so scientific notation, got to hack these big numbers. Okay, so your answer on your calculator is going to give you this, 4.57 times 10 to the 14. Now, if you split that 10 to the 14 into the 10 to the 2 times 10 to the 12, the 10 to the 12 will give you terahertz. All right? Tera anything is 10 to the 12. All right? So we're going to keep this 10 to the 12 here, but this 10 to the 2, I'm going to 10 to the 2, that's equal to what? 100, yeah. Okay, so 10 to the 2 is 100. So 4.57 times 100, ding, 457. So basically what I do with this, I decrease 10 to the 14 by 2, and I move this decimal point 2 points over. 457 times 10 to the 12. And that is why the answer for this one is 457 terahertz. All right? Now let me pause for a question. Yes?
Could you demonstrate its calculation on the calculator?
No, because I don't have my calculator. I know, sorry. But you know, you got to use the EE button. I'm going to turn the lights on. You guys are going to be able to do it. Yeah, you're going to have to figure it out. But you can do it on pencil and paper this way. You know. Question.
Can you go over again why you went from 17 to 14?
From 12 to 14?
No, from 10 to the 17.
Yeah, because this one here, look at that, 3 divided by 656. That's 0.00457, I think. Is that right? Just do this, do just this fraction here. 3 divided by 656. It should be about 4.57. No, 0.00457, right? Yeah, all right. Question. Definition of nanometers. So whenever you see this, you write in this. Okay? Yeah, nanometers. And you guys, visible light, we usually work in nanometers. Okay? If you're working in X-rays, maybe not, but visible light, nanometers. Question? Go ahead. That's the speed of light. That's a constant of nature. So you got to memorize that one. Or put it in your notebook and put stars around it. What is 3 times 10 to the 8? That's the speed of light. 3 times 10 to the 8 meters per second. Question?
Wait, so you said divide 3 by 656 and that equals
0.00457, I believe.
I keep getting 4.57.
Yeah, you're in scientific notation on your calculator. So you can do, you know what you can do is just do this, and you'll get it. Do this on your calculator, and you'll get this, 4.57 EE14. Or it'll just have 4.57 and then a little 14 in the upper right. All right, now, first I click, oh, one more question.
If you'll go back, I don't understand how you got the 10 to 17.
10 to the 17? Yeah, 10 to the minus 9 in the denominator is like 10 to the regular 9 in the top. And you've already got 8 up here, 10 to the 8. Yeah. Yeah, that's what I do. That's what I do when I'm working on paper. Okay, question number 1. Here we go. Visual IQ test. Multiple choice. How many waves? 1, 1.5, 2, 2.5, or 3? This is going to be interesting. Oh my goodness. One, 1.5, 2, 2.5, 3. Good. I'm glad you guys are This is excellent. Oh my goodness. 1/2, 2.5, 3.5. No, we don't have 3.5. We only have 3. Somewhere between 1 and 3. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And get your answer in before my right hand clicks. And you know what? You guys are the major. I can't show you this, but the majority of students, the biggest group voted for D. Now let's take a look at what we got, and that's good. D is the correct answer. I see a bunch of people going like this. That's great. All right, eyeballs, eyeballs. Eyeballs. Now look, now let's take a look at a wavelength. See, this is a visual skill, so use your eyeballs to look at what I'm doing here. Okay? Eyeballs. Everybody look. Make sure you're looking.
Okay, there's a wavelength. Right? Peak to peak. Okay. Now let me park it down here at point A. Oops. I went the wrong way. Okay, here it is. So from point A to point whatever. Okay, that's one full wavelength. Right. Here's another one. Watch what I'm doing. All right. That's a second one. And then over here, ding, just like you were saying. One more, and it's only a bump. It's half of the wave. So you got two full ones and half of the full ones. So it's 2.5. All right. It is 1:20. You're dismissed, and we'll do some more calculations on Thursday. No homework. Go ahead and get it. I'm getting easy in my old age. No homework for 2 days in a row. Gosh. That means we're going to get 3 times the homework, aren't we?
Yeah, that is what it means. The next time I give you homework, it's going to be a pile. That's